Welcome to Chapter 13, where we will be talking about equilibrium, and we want to start by defining what reaction equilibrium is. So we've now talked about how chemical reactions actually occur. You have a mechanism with a sequence of elementary steps, atoms, bonds breaking, atoms rearranging, moving around. So you could look at a reaction like CO and H2O combining to produce CO2 and H2. And we can predict and think about the changes that drive that or how that reaction occurs. And if all of those steps can happen such that carbon monoxide and water combine to give you CO2 and H2O, it has to be possible that that can also happen in the opposite direction. That CO2 and H2 could combine to give you the same carbon monoxide and water that you started with. Every reaction can be written in the reverse direction, where what you are calling previously, we just said these were the reactants and they would change and become these products. But molecules don't know what you call them. So instead, these things, which you previously called the products, could instead be the reactants and change into products, right? The other molecules, right? Basically what we're getting at is if you define a reaction that, set of molecules A can turn into set of molecules B, then it has to be possible that the opposite change can also happen. So if we think about actually performing a reaction, I'm going to put just my reactants in, right? I have control over how I set up what molecules I mix together. I'm going to put carbon monoxide and water together in my mixture. And they're going to start to react and become what I call products. And it is important to note, we're still going to use this language, reactants and products. Even though, molecules don't know what they are, that's still going to be useful for us just to all be on the same page. When I write a chemical reaction like this, the stuff on the left is the reactants, the stuff on the right we're going to call products. So they're going to start reacting. This is my reactant pair becomes products. I get CO2 and H2. And this just continues, and I get more and more product. Right? There's some product, chemical reactions. And eventually I get what I would call my reaction mixture. That's a combination of product and reactants. This always happens because we know that chemistry doesn't just happen immediately. Even fast reactions have some sort of time scale, right? There is always some sort of time scale. You mix the reactants together and it takes time for the product to start to grow. It takes time for the reactants to react and become product. So you will always generate a reaction mixture where there's a combination of product molecules that you started with and reactant molecules that you started with and product molecules that you've made. Some reactants have changed, but not necessarily all of them. Now that there are products, the CO2 and the H2 in this case, that exist, they can start to react in the opposite direction. We know that reaction rate is based on concentration. You have increased the concentration. It was at 0, so the rate would be 0, but now it started to increase. There is some CO2 and some H2, and so you will have that reverse reaction starting to occur. And this will just happening at the same time that the reactant molecules are still reacting, right? They're still present. They can still react. And so what happens is you have a dynamic setup where in this reaction mixture, both directions are occurring, the forward reaction and the reverse reaction. It is dynamic. And eventually, you're going back and forth at the same rate. They're going back and forth, and eventually they would reach the same rate. Okay, eventually you would have the forward rate and the reverse rate happening at the same pace. Basically, the change of concentrations becomes the same, which means the relative amounts stop changing. Basically, the rate of forward, so taking reactants and turning them into products, is equal to the rate of the reverse, taking products and turning them into reactants. If those are equal, they just stop changing. So if you have only reactants, right, you just mix CO and H2O, only the forward reaction will occur. If you put only products in there, if you mix CO2 and H2, only the reverse reaction will occur. There is some happy point in the middle where everything is there. You have a mix of reactants and products where the concentrations stop changing, and we call that equilibrium. So this is chemical equilibrium is defined a couple different ways. But what it means is that in a reaction mixture where the forward and reverse rates are equal, which means that all of your concentrations are constant. It's important to note that you have both or all of your reactants and products are necessarily present. So there's at least a little bit of everything that is present. It's not just only reactants or only products. So that's one of the first takeaways from chemical equilibrium. You never get only products or only reactants. At chemical equilibrium, there's always a little bit of something, and their concentrations are constant. That is where we stop seeing a change. We stop seeing the effects of a chemical reaction because we have constant amounts of reactants and products present. You'll note when we write the chemical equation, there's this double arrow that's used. That double arrow indicates that this reaction is in equilibrium. Every single chemical reaction is always in equilibrium. It's just sometimes the small amount of reactants or products is on the order of, thousands of molecules, which isn't necessarily relevant. But in this case, there is always, when in reactions where it really matters, where they are a good mixture, we always want to use a double arrow, or where we're talking about it in that means. One of the things about equilibrium is that it doesn't matter how you start. You always reach equilibrium. You're always going to have an equilibrium mixture where you have both reactants and products. So this reaction, I have the SO2, I have O2, and I'm making SO3. So those are the colors. And so you can see if I start with basically the green and the red has high concentrations, that means I start with only reactants. Well, those reactant concentrations decrease and you make products. Right, and then you get to the equilibrium and you can see they start changing, right? We looked at kinetics was where your concentrations were changing eventually they reach a flat point where they're flat. That's where equilibrium is. That's what we mean that the concentration stops changing. It's just a constant value over time. And it's important to note it doesn't matter if you started with, say, only product, say only the yellow line, eventually still everything flattens out. And you will note that across these two graphs, you had different initial conditions, right? Only reactants or only products, but they've reached the same equilibrium. You have the same relative amounts of O2, SO2, and SO3. You can see that the yellow line at equilibrium is the highest for both sets of conditions. It's just a matter of what you started with. And what you started with, how the relative shift occurs is what you started with, but equilibrium is always going to be the same. That sort of balance is always the same requirement. One thing that's important to remember, though, even though the concentrations are all staying the same, the reactions don't stop. Molecules are all in this reaction mixture. They're all still colliding. They're all still undergoing changes. And so if you have this reaction mixture, say 2NO2, the small molecules, combined together to give the N2O4, the big molecules. And so you could have, say, this pair of NO2 on the left and the N2O4 on the right. And what we say at equilibrium is that they both change at the same rate. So you have an overall constant concentration, not necessarily the exact same reactant molecules. It's not that you hit like I have these 20 reactant molecules and they're just never going to change. They're still changing, right? What makes the specific atoms making up those 20 reactant molecules is dynamic. It's fluctuating. But the rates are staying at the same pace.
Participation 215, question 1. Rewrite each of the following false statements to be true. A, at equilibrium, the rate of the forward reaction is slower than the rate of the reverse reaction. B, the mixture of reactants and products at equilibrium depends on the initial reaction mixture. And C, at equilibrium, all molecules stop reacting. This is the first question on participation 215 due Tuesday, February 15th at 11:55 p.m. over on Blackboard. Link to the assignment is where I upload links to these videos. Again, rewrite each of the following false statements. So they're all false. Just want you to rewrite each of them to be true. At equilibrium, rate of the forward reaction is slower than the rate of the reverse reaction. Mixture of reactants and products at equilibrium depends on the initial reaction mixture. And at equilibrium, all molecules stop reacting. All of those are wrong. How can you rewrite them to be correct? All right, got our first participation question already on this video. We want to find some more across the rest of these. This first set of videos, the start of chapter 13, will also be covered on the week 6 homework. And then we will take a look at also the chemical equilibrium lab on Wednesday, all about chemical equilibrium, as the name implies. So we will take a look at that. Also, later this week, got the second set of videos, weekly homework, post-lab due over the weekend. If you got any questions, let me know. Otherwise, welcome to week 6, chapter 13, all sorts of fun stuff. See you in the next video.